Okay, here we are. As you must be aware, we are working with this very interesting and exciting series of videos related with fundamental concepts, basic concept of power engineering. Those videos are dedicated for these students that they are just starting to the amazing field of power engineering, and they need to understand the basic concepts. And one very elemental, fundamental, basic concept that you need to understand is the transformer. And today we are working with a power transformer, ideal power transformer. So without further delay, let's start by reading this statement. A 5 kVA single phase transformer. Let me put here the notation. This is an ideal single phase transformer. Has a turn ratio of 10:1 and is fed from a 2.5 kV supply. Neglecting the losses, of course we are neglecting the losses because this is an ideal transformer. Determine A, the full load secondary current, I2. B, the minimum load resistance which can be connected to the secondary winding to give full load kVA. Very interesting and very useful question. And Z, the primary current at full load. To be honest, the three questions over here, they are extremely relevant if you are sizing the cables for the primary and the secondary winding of this transformer. But let's start the explanation. As you can see over here, the first step is we need to recognize, we need to know the transformer ratio. The transformer ratio is explicitly given here, as you can see at the statement, 10:5. So here we know that the transformer ratio is equal to 10. So now what is important is that we know the primary voltage, and the primary voltage is 2500 volts. So using the transformer ratio, we already know the transformer ratio, that important rule that defines how the electrical quantities in the two-winding transformer are modified. So using the transformer ratio, we can calculate the secondary voltage. And the secondary voltage, you can see over here, that is, the secondary voltage is the primary divided by the transformer ratio. In this case, you can see over here that 10 is the transformer ratio. So it's simple to identify, simple to see that the secondary voltage is 250 volts. Next step is, well, we know here this is a step-down transformer. We know this is a step-down transformer. We are going from this voltage that is 2500 volts to a voltage on the secondary that is 250 volts. But also we know that the apparent power, the rate apparent power of this transformer is 5000 volt amps. So it's very simple for everyone in this video to calculate the secondary current dividing the rate power by the secondary voltage that we already know. So 5000 volt amps divided by 250 volts. Well, we obtain here the secondary current, and that is the rate secondary current because this is the rate power of the transformer. So this current is defined at the secondary side of this transformer, 20 amps. This current is extremely important because if you are sizing the cables, the wires, the equipment that they must be connected at the secondary of this transformer, you will be using these 20 amps as the main indicator to specify the cross-section area of the cable used in this problem, okay? Next question is quite exciting and also very useful, because as you can see, we are asking for the resistance that we can connect on the secondary, the minimum resistance that we can connect over here in order to get these 5 kVA or 5,000 volt amps delivered. So what we need to do is using the basic Ohm's law. And if you remember, the Ohm's law says secondary voltage is secondary impedance multiplied by the secondary current. So we can define the resistance as the ratio between 250 volts that we are having here plus the current that is moving around 20 amps. So we obtain here the resistance that we can install in the secondary winding to mimic the full load of this transformer. And as you can see, this is a 12.5 ohms. Final question, and very simple, is to calculate the primary full rate current. And to do that, we already know here the secondary. So we apply the transformer ratio. This is the transformer ratio. So dividing the 20 amps moving here at the secondary, this is a step down transformer, dividing by the 10, that is the turn ratio. We obtain here the solution, and the primary current in this transformer is equivalent to 2 amps. So now we have here the current that must be used for designing the cable that will be used on the primary side. As you can see, this is a very simple example, but this example is extremely useful to specifying other devices that will be used together with the transformer, something that you will be doing if you are in the industry, if you are in the utilities, electricity utilities, or somewhere where you need to install a transformer to deliver electricity to your load. So we are reaching the end of this video. This has been a very short but very useful video for all of you. I hope you enjoy, and if yes, please subscribe to the YouTube channel, subscribe to the social media, and be part of our community. And it's time to say the classical and very well known bye now.